Yeah. You continue. Yes, so now usually you have kind of observed. So it's my pleasure to introduce the speaker of our seminar today,
Sorry.
Georgy Sharygin from Moscow State University Lomonosov. He already visited the Prague and Hradec Králové several times. So he's very welcome here. We have very many time
No,
fruitful discussion.
somehow I cannot demonstrate I cannot see my screen. Do you see whiteboard? Sorry, just before I continue.
We see your screen now.
Not
the whiteboard. So
I want
to share again.
I want to share my whiteboard, not my screen with you. Sorry. Somehow I cannot do this.
You cannot do it.
I just want
you
to
already
turn
write
on
something and
yeah, sure, but I want to turn on my whiteboard. Oh, now it runs. Sorry, it was some fleeting mistake. Yeah. Okay. Okay, now everything.
You can start.
Yes.
Yes. So we have we are good friend, and not only good friend. I profit personally from mathematical discussion. Is Gosha. So he's very welcome to our seminar, and he shall speak today on around the noncommutative cross ratio. Please.
There is some noise. Okay. Sorry, let's go on. So I'll begin with elementary geometry. That's, I like elementary geometry, so I always begin with it. With your permission, I do it here again. So I'll begin with reminding everyone the notion of cross ratio in its original elementary geometric form. So we begin with the usual ratio of 3 points on the line. So we have 3 points. Sorry. Something is wrong with my tablet. I'm sorry, I have to, I don't know why, but my tablet seems to work improperly. Let me try to restart it again. Okay, so we have 3 points on a straight line, A, B, and C. So let us call them A, B, and C as they should. Don't know, but for some reason my tablet doesn't work. It's probably because my daughter used it. I had to check it later. Sorry. What's wrong with it? Let me restart my my screen. What's wrong? I'm sorry for this, but something is wrong with my tablet. I don't know what is going on. It usually works much better. Please let me just spend some time trying to turn it correctly.
Okay, yeah, I mean, just we still have time, Gosha, so don't worry.
Something is wrong. I don't know why, but it used to work much better yesterday when I used it to deliver lectures.
Maybe that I see that on the in screen. I think that's from your screen. That internet connection not stable. Maybe it's because
internet connection is not stable. I don't know why, but yeah. But maybe that's the reason. I don't know. Okay, let's try it. Okay,
yes.
So we have 3 points in the straight line, A, B, and C. And now we introduce the double ratio of this, the usual ratio of these 3 points. Namely, we introduce lambda of A, B, C. I don't know what's the reason for this. Maybe I don't know what happened to this. Maybe that's because of the internet connection. I don't know. It's almost impossible to draw anything with this. I'm so sorry. Just want to ask my family to turn off their computers right now. Maybe that's the reason why. Sorry, I hope that the problem will be solved soon, but I'm not sure. Okay, let me try it again. So let us have 3 points, A, B, and C. I don't know. I don't. I don't know what happened to it, but I try to do my best. So let us have 3 points at one straight line, and we call their double relation the number lambda, such that if we have vectors A, B, A, C, and A, B, and lambda times, say, A, C, I'm sorry, I think that's because I have to, I use my camera. My internet connection cannot support both tablet and camera. So with your permission, I'll turn off my camera. Okay, sorry. Yeah, it now works much better. AC is equal to BC. Okay. Okay, then, great. Now that was the reason why I couldn't use my tablet. Okay, I hope that now it will work perfectly. So that's a definition of usual double ratio, usual ratio of 3 points. This ratio has lots of nice.
Sorry, do you mean AC equal lambda BC?
Well, it can work both ways. So I use this notation. But you can use different. Then you have to.
What do you mean by this equality, by this vector equality?
So it's just coefficient. You need to write down 3 points on a straight line.
So you have written the equality right, or it's okay? It's okay. The equality you have written AC equal BC or AC equal lambda times BC.
So lambda times AB, lambda times AC.
Okay, so write it right.
Sorry. Well, it depends on how you defined it. Well, actually, so this ratio has lots of nice properties. For instance, it's invariant when you take affine transformations of your plane, affine transformations of your straight line. But if you take projective transformations of straight lines, this ratio fails to be invariant. Namely, if you take 2 straight lines, and if you project from, you have 3 points A, B, and C on one of these lines, and then you project these points onto the other, yeah, then these 3 points need not have the same ratio as these 3. Right? But in order to make them invariant, one uses the following well, additional construction. One adds one more point, D, and then one introduces the cross ratio, the double ratio of these 4 points, as the ratio of 2 usual ratios. Namely, if you take the ratio of lambda ABD with lambda ABC, and this is called the cross ratio of 4 points A, B, C, D. And this is now invariant with respect to the projective transformation of the sort I have just described. So actually, you know that this is equal to A prime, B prime, C prime, and D prime. So this is very well known, and the proof is easily obtained from geometric consideration. Namely, if you take areas of the triangles, so if O is the center of our projection, then if you take the areas of triangles, say, OBC and triangle ABC, OAC, and what you obtain will be equal to lambda. Well, especially if you take oriented triangles. Now the same is true for triangles OBD and OAD. And of course, now you can rewrite the areas as the products of sines of certain angles. So I just put alpha here. So of course you understand what kind of angle you use, times the length of the corresponding so OB times OC, and the same the bottom, same in the denominator. So ABC. Oh, sorry, not Z. That's that should be sorry, OA. AO times OC. Now OC is cancelled out, and if you do the same thing with the top, with the lambda of ABD, you'll see that everything will cancel out except for the angles, and the angles are the same for both primed points and non-primed points. So this is invariant. This ratio, this number cross ratio of 4 points, is the simplest and the most important projective invariant. So, and of course, now that we have defined it geometrically, we can now reproduce the same definition in pure algebraic way. Actually, if we introduce coordinate z of the point on the straight line, then we have the following formula. So first we have z a minus zc. Za is the coordinate of the point A. We divide it by zb minus zc. And then we take the product with zb minus zd divided by za minus zd. So this is the way you write down this expression in coordinates. And of course, this formula implies that you can go from real numbers to complex numbers and to any other field of coefficients if you want. Right. Moreover, as I have explained, this expression, this formula, is invariant with respect to the projective transformations. So we can actually write it down in terms of homogeneous coordinates of points in the projective line. So if z comma w are coordinates, are homogeneous coordinates in projective line in P1, then the same formula is rewritten in the form of the following expression. So A, B, C, D is equal to ZA WC minus ZC WA, and so on. So in the bottom, we shall have ZB WC minus ZC WB times ZB WD minus ZD WB divided by ZA WD minus ZD WA. This is a very nice formula. As you see, you have just some determinants of 2x2 matrices here, which you can easily reinterpret as areas of certain triangles, and that's why this triangle, these areas actually appear in our proof earlier. Okay, now the main idea is that we can actually, we want actually to extend this definition from projective spaces, projective lines over fields to projective lines over noncommutative rings of coefficients. So we want extend to projectivizations of some non-commutative rings. Of course, in order to have projectivization, we need to assume that whatever we want something to be invertible, it is invertible. So most natural thing to assume is that our non-commutative ring is actually a non-commutative field. For instance, what we can consider the example of non-commutative field, such commutative field as quaternions. But it's not uniquely this field we shall consider, because it is there are more examples than just that. And moreover, if you just assume that everything is invertible, then it is also quite enough. So before we do this, I just want to tell you a couple of words why this invariant, why this number is really important. So actually, I want to give a couple of properties which we would like to preserve while generalizing this to non-commutative setting. So properties we want to preserve are the following. So the first property is that kappa should be invariant with respect to projective transformations or Möbius transformations. So Möbius transformations is another word for projective or linear rational transformations. Second thing we want to have is that kappa should be the unique invariant of a quadruple of points. Namely, in geometry, we know that any 4 points in a projective line can be identified with the help of Möbius transformation if and only if their cross ratio are equal, if their cross ratios are equal. So we want to have the same property here. So let us put it this way. Kappa determines the 4 points up to a Möbius transformations. Möbius transformation. Okay, and the third property we'd like to preserve is the famous, it's sometimes called 5-term relation, but I prefer to say that I would like to say that we want to prefer to preserve the way kappa is transformed under the action of the permutation group S4. Namely, if you take kappa, not of A, B, C, D, but say of A, B, A, D, C. So we change the order of A and B and also of D and C. And if you look here, you'll see that nothing changes. So actually, when you exchange B and A, is this, sorry, A, B, C, D, yeah. Yeah. Is this right? Just want to check it with myself. I think it is. I think, no, it's actually, well, up to, yeah. Maybe you should take the inverse here, right? If you change the order, yeah, if you change both A, B, B, then this changes with this, right? But it also change A and C and D, so it's actually the same, right? And similarly, if you but if you change, for instance, the order of the first pair of points with the second pair of points, for instance, if you write, if you write AB, but change the order of the second pair of points, DC, and what you obtain is the inverse of A, B, C, D. And more generally, if you, for instance, change the order of B and C, sorry, not, yeah, but also need to change the order of C and D before that. And what you obtain will be even more complicated formula than before. So it's 1/1 minus kappa FBC ABCD. So I want to, and there are similar formulas for all possible reordering of points. So I want to preserve these three properties. And so the first thing I would like to tell you is how this can be done. To this end, we consider one more definition of the cross ratio of 4 points. Namely, for every point A in a projective line, we choose its preimage in, let's call it X, for instance, in, say, R2. So here R is any coefficient ring. It's just choosing the homogeneous coordinates. Then we have, instead of 4 points A, B, C, D in projective line, we have 4 elements in this two-dimensional space, so to say, X, Y, Z, and well, let's call it T. That's how this is done in the original paper. Then, if we want to define the cross ratio, we consider the following system of linear equations. These linear equations allow you to express one element in this two-dimensional space as a sum of 2 other elements. For instance, we can, we want to express Z as some alpha times X plus beta times Y. And similarly, we express T, probably, yeah, I think it should, I should better use alphabetic order. So I use T, and here I use Z. Then here we can express Z as, say, gamma times X plus delta times Y. And then if you just remember the Kramer rule, you'll see that the formula star is just a ratio of the coefficients in this equation. Actually, kappa of ABCD will be equal to the ratio of Well, up to the order which I might have mistakenly changed, but up to this, of these 4 coefficients. So up to this, up to the reordering of the elements. Great. So we can now use the same approach in non-commutative setting very well. So let's assume that we have 4 elements x, y, z, and t, but now in non-commutative space, plane, I would say, of a non-commutative ring. In this case, we shall have to choose the order of vectors and coefficients in this formula. So I would stick to the right order. So I mean that although in this formula I wrote coefficients on the left of the vectors, in what follows I will always write coefficients on the right of the vector. So this equation, let's call it 1, in non-commutative setting will look like t equals x times alpha plus y times beta, right? And z equals, of course, I can write it as x times gamma and y times delta, but just to save, well, since we will have to divide one over another, I'll do this exercise at once. So I write it as x times alpha times some coefficient gamma and y times beta times some new coefficient gamma, so this is, I mean, the same coefficient gamma, and times kappa. And this kappa is now the cross ratio. Namely, and I mean, of course, it is just our free will to call this cross ratio, but the reason for us to use this free will is the following theorem. Very simple theorem, but a little bit unexpected. The properties which I listed at the previous page, 1 through 3, hold here. Let me use a red marker to underline this. Well, hold up to conjugation. So let us explain this. So first, the property number 1. It is the easiest property, actually, at least, well, if you know the formulas. So as far as the projective transformation are concerned, projective transformations on the level of the plane are given by linear transformations of the plane. So when you take a projective transformation of the plane, it means that you have to multiply every element x, y, z, and t by some non-degenerate matrix, 2 by 2 matrix, capital G with coefficients in R. So let G, oh, sorry, capital G, be an element in GL2. Then, of course, if you multiply x, y, z, and t by G on the right, not just the cross ratio will survive, but even the coefficients alpha, beta, gamma, and delta and kappa will survive. So it means that kappa of x times g, y times g, z times g, and t times g is equal to usual kappa of x, y, z, and t. So this is easy. As far as the, but there is one more thing we need to prove. We need to prove that this cross ratio actually descends to the projectivization of this non-commutative plane. Well, if we want to allow the right GL2 action on the plane, and we want to, well, we want this action to be linear in some sense, we need to introduce left action, left multiplication by elements of R. So we want to show that for every four tuple of elements, lambda 1, non-zero elements, of course, lambda 2, lambda 3, and lambda 4, sorry, not T, lambda 4, in R, well, of course, invertible elements, so I put cross here. The cross ratio of lambda 1x, lambda 2x, y, sorry, lambda 2y, lambda 3y, z, and lambda 4t is the same as the cross ratio of x, y, z, and t. To do this, we need to give a more explicit formula for the cross ratio. And here I come to a very nice notion called quasi-determinants of elements in of matrices with non-commutative entries. This notion was first introduced in 1990s by Gelfand and his disciples. And well, there are different ways to introduce it, but I use the most explicit one. I just write down the formula, which we use in our talk, we'll use in my talk. Namely, let A11, A12, A21, and A22 be a matrix in with coefficients in R. I will assume that well, at least one of these entries is invertible, and well, for instance, suppose that A12 is invertible. Then I put this entry into the box, and I call the following expression the quasi-determinant of this matrix with A12 boxed. Sorry, I have to assume that A21 is invertible. So I'm sorry, I'm boxing one, and I assuming that invertible is the opposite. So whenever I box something, it means that the opposite one is invertible. So actually, now I can write down the formula. A12 minus A11, A21 minus first A22. It is easy to remember this formula if you imagine that the elements in the entries in this matrix maps in some well category from elements with indices 1 to elements with indices from element with index 1 to element with index 2. For instance, here I have a map from element from index 1 to element from index with index 2. And if I take this as a composition, that the first entry, A22, sends, so A22, first from the right, I mean, sends element A2 to A2, sorry, is this correct? Yeah, it is. Oh, so it's opposite direction. To A2, then A21. It used to send element from 1 to 2, but now we invert it. It sends element from 2 to 1, and then we use A11 to pull it further into A1. So both terms in this sum send A.
Gosha,
Yeah.
is it the first
From right to
transformation?
left. Yeah.
What is the first transformation? Multiply
So,
A2 to by is A2.
So this is product. Of course, if you work with a ring, non-commutative ring, this is just a product.
Okay, okay.
But in order to remember the way you compose these elements, you should imagine that every element is a map from, well, from right to left and from left to right. Doesn't matter actually. If you read this from right to left, it should go from A2 to A1.
Yeah, okay, thanks. Yeah.
And then these, so the first coefficient, the first term sends A2 to A1. And the second term also sends A2 to A1. So this is the way you remember this. For instance, if you take this kind of boxed element, right?
Yeah, now I understand. That is on this thing. You should write the schematics. Yeah.
Yeah, sure.
I understand.
Yeah, so A21 and A22. So now this element is considered invertible, and you can write down the formula as A11 is a map from 1 to 1. And then it is a map from, say, A22 minus first, and the remaining part, 2, 1. You see? So, and so on and so forth. So you can actually write this for any position of this boxed element, assuming that the opposite element is invertible. In case your entries are in fact commutative, elements of commutative algebra, what you obtain will not be equal to the determinant, but will be equal to the ratio of this determinant. So A is the matrix without indices, divided by A21 here. So this will give you different ratio, but the same numerator. Actually, you can introduce a similar notion for arbitrary metrics with non-commutative entries. In this case, there will be n square ways you can write down this non-commutative quasi-determinant. And they all will be equal to ratios of usual determinant with some minor of this matrix. The minor will be the minor complement to the element you have chosen. If you want, I can give you this definition, but we can proceed right now. I can do this later. So suppose we have this notation, then you can write down the formula for the cross ratio in terms of these quasi-determinants. Namely, let x1, x2, y1, y2, and so on be the coordinates of the elements in R2, which we use. then the cross ratio is equal to the following expression. You begin with the quasi-determinant of y1, y2, z1, z2 with boxed z1, but here you have to take inverse. Then you take the same, but instead of z, you put t. And no inverse now. Then you have x and z, x1, x2, and z1 boxed. And then finally you have x and t without inversion. So now this formula is very convenient. For instance, it shows at once that unfortunately this is not true on the nose. This is not equal to just the cross ratio of 4 points, original points. Instead, we have a very nice equation. So this equation will look like this. If you take kappa of lambda 1 x, lambda 2 y, this is y, lambda 3 t, sorry, lambda 3 z, yeah, but x, y, z, t, and lambda 4 t, then it is equal to lambda 3 minus first kappa of x, y, z, t, lambda 3. So in particular, if our ring is commutative, this will turn down to, will boil down to the usual relation. But in general, only this expression is preserved only up to conjugation. So this accounts for the property number 1. As for the property number 3, I prefer to begin with it. That is the way this expression is transformed under the permutation of matrix of elements A, B, C, D. We shall also have some modifications of the original non-commutation relations, namely kappa of, if you change the order of y and x, right? Yes, and also of z and t. We shall not have just the same expression as before, but we shall have it equal to the same expression up to the conjugation. One can actually find the coefficients. I'll write it down as mu in terms of the elements x, y, z, and t. These coefficients mu also are quite interesting. They are called Quasi-Plucker coordinates. So in this case, it is equal to Quasi-Plucker coordinate x, q of z, t, y. So Quasi-Plucker coordinate, roughly speaking, is just the first pair of quasi-determinants here. But in any case, this relation boils down to the usual commutation relation, if the ring is commutative. In general, we should have a conjugation by various elements. So again, a straightforward computation shows that the permutation relations survive up to the conjugation by elements of R. As for the property 2, that is the uniqueness of our of a quadruple of elements in R2 up to
Gosha,
yeah.
what mean conjugation here?
A conjugation is just this conjugation in the say a joint action of elements.
Sorry, action. Yes. Okay.
Yes, if you prefer. Yeah, I don't know. I think it was the correct term, conjugation, but I'm not sure. Okay, conjugation by an element. Okay, so if we turn to the second property, that is the uniqueness of a quadruple x, y, z, and t with given cross ratio. One can prove a very similar result to what we had before. That is, suppose that kappa of x, y, z, t is not equal to 0 and 1, and kappa of x prime, y prime, z prime, and t prime is equal to the same, but up to the conjugation. For some mu in R cross. Cross means non-zero set of invertible elements. Then there exists element G in GL2 of R, and lambda 1, lambda 4 in R cross, such that, well, primed elements are equal to non-primed, to which you apply both lambda and G. That is to say, x prime is equal to lambda 1x times G, and so on. The proof of this follows directly from the formula I have just described. The proof follows from this formula. So this is Q y z t. So if you just now look at this formula, then choosing G so that y is equal to, say, 0, 1, and x is equal to 1, 0, we can express, such that y times G, of course, and x times G. Sorry. We can now express this cross ratio, if you do look at this, as the following combination of coefficients of t and z. So I think it is something like T1, T2 minus first, Z, yeah, Z1, Z2, Z1 minus first. Yeah, I think it is like this. So, I mean, of course, these coefficients are coefficients of Z and T after the action of G. We can also choose similar G for G prime for the primed elements. X prime G prime is equal to 0, 1. And same for Y prime. Yeah, 1, 0, 0, 1. Then we have a similar relation up to the conjugation here. And now one can just solve this equation by introducing coefficients lambda 1, lambda 2, lambda 4, and so on. Okay, so I can give you reference to the paper where this is done, but I hope that up to some exercise, this statement is more or less clear. So very nice. We have introduced this cross ratio, and it turns out that this cross ratio in many respects is as good as the cross ratio in usual geometry. For instance, one can find many classical applications of cross ratio, and these classical applications in many cases can be reproduced in non-commutative setting. One of such applications is the famous pentagramma mirificum by Gauss. It has beautiful geometric description. I'm not going to explain this geometric meaning like right now. But in terms of cross ratio, this pentagramma has the following meaning. Let us denote, let us have 5 points in projective line, for instance, in complex projective line. Let us call them P1 through P5. So let P1, P5 be 5 points in CP1. And let us denote by xi the cross ratio or minus cross ratio of pi plus 1, pi plus 2, and so on. Of course, I use cyclic order of these points. Then the following is true. xi times xi plus 1 is equal to 1 plus xi plus 3. This is the classical result by Gauss. In non-commutative case, however, we have very similar result. Well, modulo some permutation of indices. I'm not going to reproduce this permutation right here, but just give the following most general description. So suppose we have 5 points in, well, this time is R cross R, R2, right? We can introduce not one, since our cross ratio changes not just by okay, since when we permute elements in cross ratio, we don't just obtain cross ratio up to taking inverses and so on, as in classical case, but also we obtain cross ratio up to conjugation. We shall need to introduce not 5 points x1 through x5, but 10 points. Namely, we put x1 equal to minus kappa of P1, P2, P3, and P4. X2, well, X2 will be equal not just to, as you can expect, P2, P3, and so on, but it will be equal to something more complicated. That's because our notation is not perfect, unfortunately. So it's something like P5, P2, P3, P1, and so on. So we have 5 points like this. And we shall also need 5 more points with bar over them. X1 bar will be equal to minus kappa 2, 1, 3, 4. So actually, we just change the order of the first 2 elements here. We need to do this because we don't have so nice properties of cross ratio as before.
Gosha, 5 minutes more, okay?
Okay, I just do it like this and P4. And so on. So X2 will be obtained, X2 bar will be obtained by the same way, in the same way from here. So it's just minus kappa of P2, P5, and so on. Yeah. Then we have the following relation. So it used to be xi times xi plus 3 is equal to 1 plus x, sorry, xi plus 1 is equal to 1 plus xi plus 3. But now we shall have the following. X say 1 times conjugation by certain Plucker coordinate. I put it mu in general case. X3 mu minus first will be equal to 1 plus x2. And at a certain moment, we shall have a bit different relation, like x5 times some conjugation with some different coefficient of x1 bar will be equal to 1, sorry, x2 bar, 1 plus x1 bar. So as you see, we cannot, in this case, reproduce 5-term cyclical order, cyclical permutation, but we can reproduce a 10-term cyclical permutation in this case. Well, since I'm already running out of time, I'm afraid, I cannot explain everything I wanted to, but let me just mention a few more things which hold for the non-commutative cross ratio. So properties So first, there exists non-commutative version of how do you call this, cyclic cocycle equation. More or less, it is the following. If you take kappa of x n x1 zt, and then you multiply it by kappa of xn minus 1, xn minus 1, xn, zt, and so on until you come to kappa of x1, x2, zt, then it is equal to 1 for all x1, xn, zt. Second property, which also survives, is the relation of cross ratio with Schwarz derivative. As probably you know, if you take 4 points, if you have a map F from a projective line to projective line, say complex or real projective line, and you take a point X in this projective line and take points X plus epsilon, X plus 2 epsilon, X plus 3 epsilon in this projective line, and look at the image, right? Apply F to both, to all these 4 points, and look at the image and take the cross ratio, f of x, and so on, f of x plus 3 epsilon. Then you know probably that this is equal up to the third order of epsilon to the Schwarz derivative of f. And Schwarz derivative is the measure of f being equal to the Möbius transformation. So S of f is equal to 0 if and only if f is Möbius. In this case, in our case, we also have a kind of Schwarz derivative for any map from, well, but this case we need to take a map from real projective line, for instance, to non-commutative projective line. So let's put it like this way, RP1 to P1 of R, where R is non-commutative. And we again have a Schwarz derivation of f, which also appears in this way. But this case, so in classical case, Schwarz derivation used to have the form f triple derivation of f divided by f prime minus 3 over 2, I think, f double prime divided by f squared, f prime so squared. In this case, we need to choose the order of elements in this product. So you need to fix this order, and this order is fixed uniquely by this property. The most interesting is that the formula up to this choice is uniquely determined. It appears very naturally. And again, if f is Möbius, then S of f is equal to 0. But we don't still know if the opposite is true or not. Further, one more thing before I leave off. Number 3, property number 3. It turned out, later we found this in book, that if R is actually the algebra of some operators in Hilbert space or just of matrices of operators, then actually it turned the notion of non-commutative cross ratio has appeared earlier in papers by Zelikin, and even earlier than that in 1960s in a book by Hua Ken. There is a geometric way to, if you have an algebra of operators, and there is a geometric way to describe a cross ratio of 4 operators in terms of compositions of these operators, compositions of certain maps. And our notion of non-commutative cross ratio coincides with that one. Well, up to permutation of these operators, which I'm not going to reproduce now. And let me conclude again with geometry. In classical geometry, cross ratio can be used to describe the mutual position of points in projective plane. For instance, it's well known that if you have 4 points in complex projective plane, that their cross ratio is real if and only if these 4 points belong to the same circle. So 4 points A, B, C, D is real if and only if their cross ratio is real. If it now take, so not in R actually, they belong to CP1. If we take now 4 points, well, 5 points or 6 points, A, B, and so on, till we come to F. In projective quaternionic plane line, we can ask more than that. We can ask if 4 of them belong to the same circle, or if 5 of them belong to the same two-dimensional sphere, and if 6 of them belong to the same three-dimensional sphere. And it turns out that all these properties can be phrased in terms of non-commutative cross ratio of 4 quaternions. Ratio criteria of cosphericity. So I believe that this is already quite interesting. It deserves further investigation.
Very interesting, yes.
Yes. Okay. I'm sorry for being a little bit for wasting so much time on my tablet in the beginning. I think it was because my internet connection is not good enough to support both camera and the tablet. I'm sorry for this. So next time I'll be more cautious. That's all.
Yeah. Thank you very much, Gosha, for a really beautiful lesson and talk. So let us thank the speaker.
Thank you. Thank you.
Yes. So that is a begin from elementary spoon geometry to non-computative geometry, including operator in bare space. Yes, and there may be more application, but already for theory of operator in I only in base space. You can take more, right? Any Banach space or Fredholm operator. I don't know. Yes.
Yes, actually, you can apply this to more or less arbitrary. It's not necessary to use Hilbert space operators.
Yes.
You can use it more or less in more general situation. Actually, you can work with general noncommutative algebra. So operators are just a particular case. I just mentioned this because it is remarkable that similar constructions appeared earlier in different contexts. I just think it was a remarkable way to observe this. Remarkable enough to observe this.
Could you, I think that's your reason already appeared in archive, right? But I didn't see in the abstract.
Yes, our paper appeared in archive and it's already been published in collected works dedicated to Emma Priviato. If you just make a search, this paper appeared in 19.
Right. Yes. Could you write a reference here so that you can watch in the?
I don't remember it. I don't quite remember it. If you want, I can find this in the internet and send you reference.
Okay. So you attach like an announcement to the
yes,
video, right, Igor?
Yes, I'm sorry for forgotten to do this before.
Yes. So is there more question to Gosha talk?
Gosha, just could you expand a bit more on the last sentence about quaternions? What is known about that?
Well, no.
You know that I'm curious.
I understand. I mean, as far as quaternions are concerned, they are non-commutative. So if you want to use cross ratio to characterize the mutual position of points in quaternionic line,
yes,
to use non-commutative cross ratios, right?
Right, sure.
So if you take 4 points, for instance, A, B, C, D, then the same thing survives. You see, it is remarkable. The problem, since real numbers are in the center of quaternions, this property that 4 points belong to straight line if and only if their cross ratio is real, survives under conjugation.
Yes.
So actually, this property is precisely the same in complex and in quaternionic case. If you have now 5 points,
yes,
A, B, C, D, E, A, B, C, D, E.
Yes.
And you want to E, right? If you want to A, B, C, D, E, and then you want to check if they belong to the same sphere, then it turns out that they belong to the same sphere if and only if the cross ratio of A, B, C, D commutes with cross ratio of A, B, C, E.
Okay.
So this is another way to characterize.
If and only if?
If and only if.
Okay.
As far as 6 couple of points are concerned, I don't remember the exact way we formulated this. It was something like, okay, there was a way to make this more look simple, but I think what we have done, 6 points, in 6 points you take three yes, I think we take 3 cross ratios, A, B, C, D, A, B, C, E, and A, B, C, F. So you have 4 elements. So these 4 elements are in, so these are three, you have 3 vectors in 4-dimensional space, quaternionic space. Then these 4 points belong, these 6 points belong to the same 3 sphere if and only if these 3 vectors are linearly dependent.
Over linearly dependent over quaternions?
No, not over quaternions. Over reals. So this is, as far as I can remember, this was our criterion. You can
And this
rephrase
is
this.
in your paper. It's written in your paper.
It's not written in my paper.
Not written.
It's yeah. It was observation we made last spring, but we thought it was too small observation to publish it separately. The paper has been written by that time. Now we are trying to collect all our observations in this. But I can send you this observation. It's written in a short
Yeah, would be
notes.
nice. Would be nice.
Yeah.
But okay, we can talk at any time anyway. So.
Sure.
Okay, if there are no question, comment anymore, let us thank the speaker again, right?
And thank you very much for your invitation. It was a pleasure to make this talk. Yes, it's remarkable how this year we can talk to each other even though we are so far away from each other.